Assalamualaikum and a very good day to everyone. Today, me and my teammates will be presenting our group project about room occupancy estimation using backpropagation neural network. Before we begin, I'd like to introduce my group members. Our team consists of Erdina binti Azhar, Nora Betul Fatihah binti Ahmad, which is myself, Zahira Aliyah binti Mat Zahidan, Muhammad Shahamizan bin Johari, and also Muhammad Danish Akil bin Khairil Anwar. We work together on this project, sharing ideas and dividing tasks to complete the analysis and presentation. In this project, we want to predict room occupancy using sensor data. Knowing whether a room is occupied helps make buildings more energy efficient by automatically controlling things like lighting and air conditioning. Traditional methods such as motion or infrared sensors can be inaccurate or expensive. Instead, we use machine learning to improve prediction accuracy. Our data comes from the UCI machine learning repository with over 20,000 entries of sensor readings, including temperature, humidity, light, CO2 levels, and humidity ratio. We apply a backpropagation neural network (BPNN) to classify whether a room is occupied based on these features. This approach can help reduce energy waste and support smarter, automated building systems. Now, we are going to talk about the problem statement. The first problem statement is uncertainty in real-time detection. Buildings often can't tell if a room is really occupied. Infrared and motion sensors can be unreliable, especially if people are sitting quietly. Number 2 is high energy consumption due to misdetection. Inaccurate occupancy detection can leave lights, fans, or air conditioning on in empty rooms, wasting energy and raising costs. And lastly is lack of intelligent automation. Most older systems can't improve on their own. That's why we need smart, database models that can detect if a room is occupied with minimal human help.
Data pre-processing. For data reduction, the dataset was cleaned by removing irrelevant columns, such as date and time, which are not related to the classification process. Then we do data normalization using Weka. The numerical features were normalized to a range between 0 and 1 to ensure that all values are on the same scale and contribute equally during model training. Lastly, data partitioning. The dataset will be split into training and testing sets using stratified sampling, ensuring that each target class is proportionally represented in both sets for balanced model development. For the first part of the code, we began by downloading the dataset directly from Google Drive using gdown. Then we imported the necessary libraries and ensured reproducibility by setting the random seed. We then split the data into training and testing sets using trend test split with a stratified split to maintain class balance. Next, we use TensorFlow to build the model. In this case, we use sequential followed with dense to build the layer. The input shape refers to input layer, which in this case is 16 neurons. The architecture then consisted of a first hidden layer with 64 neurons, followed by a second hidden layer with 32 neurons, and an output layer with 4 neurons using softmax activation, as the task involved multi-class classification.
Okay, in this section, we focus on tuning the test size to see how it affects our model's performance. The test size determines what percentage of the dataset is used for testing compared to training. Choosing this right test size is important because it balances between having enough data to train the model and enough data to evaluate it properly. So we kept other parameters fixed, which is a learning rate of 0.01, batch size of 32, 10 epochs, and the Adam optimizer. Then we tested 5 different test size, which is 0.3, 0.5, 0.6, and 0.7. So from the results in the table, we can see that when the test size was set to 0.5, the model achieved the higher accuracy of 88.01% and the lowest loss value of 0.0183. This suggests that using 50% of the data for testing gives the model the best balance between learning and generalizing to new data. So the graph on the slide also show this clearly. The accuracy curve is highest and the loss is lowest at test size 0.5. So the conclusion is overall this step help us find the most reliable setup for our backpropagation neural network model, which is BPNN, so making it more robust when predicting room occupancy in different conditions.
On this slide, I'm presenting the results of hyperparameter tuning of learning rate. The left graph shows the training accuracy comparison for three different learning rates, which is 0.001, 0.01, and 0.1. We can observe that all three learning rates reach similar accuracy levels eventually, but 0.01 reaches a high accuracy faster and stabilize well. The right graph shows the training loss comparison for the same learning rates. A lower loss indicates better performance. Here again, the learning rate 0.01 shows a quick drop in loss and maintains a lower value compared to the other rates. Below the graphs is a summary table that shows the final accuracy and loss for each learning rate values. From the table, we can see that the learning rate 0.01 achieved the highest accuracy of 0.8671 and the lowest loss value of 0.0142, which makes it the most optimal choice among the three.
In this experiment, we tuned the batch size to observe this effect on training performance. We tested three values, which is 32, 64, and 128, while keeping the other hyperparameters constant, such as learning rate at 0.01, optimizer as Adam, and epoch at 10. From the accuracy graph on the left, we can see that batch size, which is 32 on the blue line, achieved the highest training accuracy early and maintained a strong performance throughout. In the loss graph on the right, batch size 32 also showed the steepest drop and the lowest final loss. This is confirmed in the table below, where batch size 32 had the lowest loss value of 0.0114. Highlighted in green, this indicates that a smaller batch size 32 helped the model learn more effectively and generalize better in this case.
In this project, we compared three different epoch settings, which is 10, 111, and 222, while keeping other hyperparameter the same. As shown in the table, the accuracy for all three runs is quite similar, around 86%. However, the loss values show clearer differences. The run with 111 epochs produced the lowest loss value of 0.0107, which is highlighted in green in the table. Although the accuracy is only slightly lower than the others, the loss is a better indicator of how well the model is fitting the training data. Lower loss suggests that the model's predictions are closer to the actual values on average. For this reason, we selected 111 epochs as the best setting, as it offers good accuracy while keeping the loss low and consistent. You might also notice that in our training loss graph, there are small up and down spikes, even though the overall trend is downward. This is normal behavior in deep learning training. It happens because we use mini batch training, where each batch has slightly different data. The optimizer updates the weight after each batch, causing small variation in the loss. Additionally, we applied data augmentation, so the model sees slightly different versions of the images each time, which also contributes to these small fluctuations. In summary, tuning the number of epochs helped us find a balance. By choosing 111 epochs, we achieved the lowest loss without overfitting or wasting training time, while still maintaining high accuracy.
So we train 4 models using different optimizers, which are ADAM, SGD, ADAMX, and NADAM, to evaluate their impact on model performance. The model architecture and training parameters were kept consistent to ensure a fair comparison. Among all, ADAM showed the best performance with 86.68% accuracy and the lowest loss of 0.0114, indicating fast and stable convergence. While ADAMX and NADAM achieved similar accuracy, their loss values were slightly higher. SGD performed the worst in this case with the lowest accuracy of 83.94% and the highest loss at 0.1972. In the training accuracy graph, ADAM-based optimizers converge faster and more consistently than SGD. Similarly, in the training loss graph, they reach much lower loss levels, while SGD struggled to improve. This is because ADAM, ADAMX, and NADAM are adaptive optimizers. They adjust the learning rate dynamically, making learning more efficient, while SGD, using a fixed learning rate, learns slower and is less effective without fine-tuning. That's why it lags behind in both accuracy and loss.
Next, we present the results of our final testing phase. At this stage, we tested a combination of the hyperparameters that gave us the highest accuracy and lowest loss values during tuning. These are the optimal hyperparameter values that we selected, which is a test size of 0.3, a learning rate of 0.01, a batch size of 3211 epochs, and we use the ADAM optimizer. Here we show the training and test accuracy over epochs. Both curves remain consistently high, with the test accuracy closely tracking the training accuracy. This indicates that the model generalizes well and is not overfitting. On this side, we have the training and test loss. Both losses decrease and stabilize as training progresses, with occasionally spikes in test loss. Overall, the loss values remain low, showing that the model is learning effectively. These results confirm that our final model configuration achieves a strong balance between performance and stability.
In this project, we use a multi-layer neural network (MLN) architecture, as shown in the left image. The MLN architecture used in the project is a feed-forward neural network implemented using TensorFlow and Keras. The model consists of an input layer with 16 neurons, 2 hidden layers with 64 and 32 neurons, and an output layer with 4 neurons. This layered structure allows the network to learn complex relationships in the data. To train this MLN, we use the backpropagation algorithm, which is why the model is also called a backpropagation neural network (BPNN). It updates the weight by calculating errors from the output and adjusting the network backward. The model summary in the image on the right shows the structure and total number of parameters, which is 9,902 in total, with 3,300 trainable. This confirms that the MLN architecture is efficiently built, and the backpropagation learning helps the model perform accurate classification.
Okay, and to conclude, this project used a backpropagation neural network, which is BPNN, to detect room occupancy based on sensor data like temperature, humidity, and light. We found that neural networks can achieve high accuracy, which is around 88.06%, and perform better than traditional sensor-based methods. So the main benefits are higher accuracy, cost efficiency, and adaptability across different room environments. And it can also help save energy in smart buildings by automating lighting, HVAC, and ventilation system. But the limitation from this BPNN is that the model needs high quality sensor data and is more complex than basic methods. However, it is scalable and supports automation, making it a good fit for smart buildings. In the future, it could be improved further by integrating with real-time system and IoT, which is Internet of Things, for smarter and greener environments.